This is lecture 10.1, where we're going to start a chapter on solutions. We already talked a little bit about solutions back in chapter 4. We learned about the concentration term of molarity. Today we're going to learn a few other concentration terms, including percent concentration terms, molality, parts per million, and parts per billion. After that, we're going to learn about dilution, and then how we can easily convert between different concentration units, so that if we're given one concentration term, we can readily convert it into another concentration term. Okay, let's go ahead and get warmed up with a little bit of review. Our first question asks, which of the following statements are correct? The network covalent solids are usually good electrical conductors. This is false. Network covalent solids don't have anything resembling mobile electrons. So no, these are normally poor conductors. Network covalent solids often have high melting points, and this is true. You have to break covalent bonds in order to get these things to melt. Network covalent solids are insoluble in common solvents. True again for the same reason. You would have to actually separate atoms in order to get them to dissolve. And that means breaking covalent bonds. And ionic solids typically have high melting points. This is true. Ionic compounds usually have significantly high melting points, usually in the 400 to 600 degree C range. And ionic solids are often hard and brittle. This is true, the way that they pack in a crystalline structure. Metals have high electrical conductivity. This is true. We have mobile electrons, the way that metals pack together or join together. And metals are typically insoluble in water, and this is true as well. Ionic solids are always soluble in water. Well, I think we're going to have to say false. The term soluble normally means that we can dissolve up to 1/10 of a mole per liter, and there are many ionic compounds that have solubility significantly less than that. Ionic solids usually have high melting points, and this is true. I think we answered that earlier. And network covalent solids are usually poor electrical conductors, and I mentioned let's see, I believe that was A, that yes, they are poor electrical conductors. And you may know that graphite does some conducting, and that's because of the double bond that we find, but they're good about conducting electricity within those planes. And I still wouldn't call that good conduction. They actually have some conduction, but that's the only network covalent solid that has anything resembling conductivity, and it's because of the double bonds that are present. Okay, we're told silver crystallizes with a face-centered cubic cell, 0.407 nanometers on an edge, and we're asked to calculate the atomic radius of silver. Okay, face-centered cubic cell, the relationship between the radius and the length of a face-centered cubic cell is for r, for radii, is equal to the square root of 2s. Just remember, in a face cubic cell, that we have one atom in the middle of each face, and that all the atoms touch across a diagonal, and that's our two-dimensional diagonal, and hence the square root of 2s. Okay, we're after the radius, so let's divide out 4, replace s with that 0.407 nanometers, and we generate 0.144 nanometers. Next, we're told platinum has an atomic radius of 0.135 nanometers, and we're asked for the length of the side of its body-centered cubic cell. Well, now the atoms touch in a body-centered cubic cell through the center, so they touch through the diagonal in 3 dimensions. And so we have 4 radii, for r, is equal to the square root of 3s. Again, we're talking about the Pythagorean's theorem, or the diagonal in 3 dimensions, and hence we get that square root of 3. Okay, let's solve for s by dividing out the square root of 3. Let's bring in r, and as we crunch these numbers, I come up with the length of the body-centered cubic cell of 0.312 nanometers. Okay, which intermolecular forces will the following exist? And the first is sulfur trioxide, and you ever see all those oxygens, we know to suspect resonance, and so we need to draw one of these structures. And when we do so, we see that we have no leftover unpaired electrons. We're going to have, on the central sulfur, we'll have a single bond to each, or excuse me, to two oxygens and a double bond to a third oxygen. And that leaves us with a symmetric shape. And a symmetric shape means that this is nonpolar. And if sulfur trioxide is nonpolar, then what forces will it exhibit? Well, dispersion forces are the primary attractive forces in nonpolar molecules. Next we have dihydrogen sulfide, and this is a polar molecule. You can always draw it out, or you can just recognize sulfur is a central element, and it has 6 outer electrons, of which 2 are being used to bond, so that's 2 that aren't. So this is an AX2E2 geometry, which is bent, which is asymmetric, and hence this is polar. And if this is polar, the intermolecular forces are dipoles. Since you polar bonds, dipoles. Next we have methane, and methane forms a very symmetric molecule. We have 4 outer electrons on carbon. All 4 are going to use to bond to the 4 hydrogens, which gives us a true tetrahedral shape, which is symmetric, so this is nonpolar. And what's the dominant intermolecular force for nonpolar molecules? Dispersion. Sulfur hexafluoride. Sulfur is our central element, 6 outer electrons, all 6 are being used, so that means we have just the fluorines attached to the sulfur. Just one thing attached, it's always going to be symmetric, and symmetric always means nonpolar. So you know we have very polar bonds. Because of the symmetry here, we have a nonpolar molecule, and so again, that would be dispersion forces. You don't have to go very far here to realize this is a nonpolar molecule. We don't even have polar bonds, so dispersion forces. Sulfur difluoride, well, this time we do have a polar molecule because sulfur has 6 outer electrons, and this time only 2 are being used to bond, so we have 2 pairs that aren't. So it's an AX2E2 geometry. I hope you remember that notation, which was bent, and bent was asymmetric, and that means polar, and that means dipole. Dihydrogen selenide is also polar, so it's also dipole. Nitrogen dioxide, okay, I suspect resins. Let me draw one out. And I see that somewhere or another we're going to have an asymmetric shape due to that one single lone electron. We have an odd number of electrons, and that tells us that we're going to have one lone electron, and that means a free radical. If you've heard that term, it means a molecule with a free lone electron. And that does mean an asymmetric shape, at least in this instance, not in all free radical instances, but in this instance. And you know, it probably would be true in all free radical instances. I'd have to think about that. But anyway, we have a polar molecule, and so again, dispersion. Excuse me, polar molecule, and so again, dipole. Nitrogen monoxide, well, I don't have to go too far to see I have one element on one side, another on the other. We have an asymmetric shape. Asymmetric means polar, and polar means dipole. Which of the following pure solids is necessary to break covalent bonds in order to make a liquid or gas? Well, if we think about the question, to require the breaking of covalent bonds in order to turn to one liquid of gas means we're talking about a network covalent solid. So silicon dioxide, is that a network covalent solid? Yes, these are silicates. Think of quartz, and to some extent, and actually to a large extent, glass. And yes, that is a network covalent solid. Sodium chloride is what type of compound? An ionic compound. So here we have to separate ions. Carbon in the form of graphite, is that one of our network covalent solids? Indeed it is. So that would require you to break covalent bonds in order to get it to melt. Iodine is a normal molecule, and it's a nonpolar molecule, and so that's not going to be a network covalent solid. And neither is octasulfur. Okay, on to solutions. And solutions are one of our 3 types of mixtures. And mixtures, remember we had 2 types of substances. We had pure substances and we had mixtures. where pure substances had a clearly defined ratio of all the participants in them. Whereas in a mixture, you can have varying proportions. The easiest way to think of this as varying concentrations. You can have dilute sugar water, you can have concentrated sugar water. So this is one important characteristic of mixtures that separates them from pure substances. Now for a solution, we have the tiniest particles, and because of them, they remain uniformly distributed throughout the solvent. Now we need to learn two new terms here, solute and solvent. Solute would be the species being dissolved, and a solvent is a species doing the dissolving. So you got a solid and a liquid, pretty easy to tell who's a solvent and who's a solute. Now if we have two in the same state, like two liquids, then the greater quantity would be the solvent and the lesser quantity the solute. Okay, there's that term again, solvent, the dissolver, solute, the dissolvee. If they're both in the same state, then the solvent would be the greater amount and the solute would be the lesser amount. Okay, we're going to revisit concentration terms here, and first, any concentration term is a statement of the amount of solute per the amount of solution. In other words, it's the ratio of the amount of solute per the amount of solution. The difference between all of our different concentration terms is simply how do you measure the amount of solute? How do you measure the amount of solution? And that's what's going to be different in all of our different concentration terms. But they're all a statement of how much solute per how much solution. And it should make sense that that is a concentration. Okay, the first concentration term we're going to learn about is mass percent, abbreviated MM percent, sometimes called mass percent, or percent by mass. And if you've ever seen the equation for percent, it's always any percent is equal to your subject divided by your total times 100%. Again, any percent, doesn't matter if you're calculating a percent you paid in taxes. Your subject would be the amount you paid in taxes, the total would be the total amount of money you made. Or the percent you got off on that car you bought. Well, the subject will be the amount that it was reduced, if you're talking about the percent off, and then the total will be the total amount. So it's usually very easy to identify what your subject is and what your total is. Now for mass percent, and we're talking about a solute concentration, I hope it makes sense that our subject is the solute. And the total is just that, the total amount of solution. And they're both going to be measured in mass. So our mass percent, or percent by mass of the solute over the mass of the solution. And the only thing that's required is that they be the same units. It wouldn't matter if it's pounds over pounds or tons over tons. You do expect in this class, and then in most classes, it's going to be grams over grams. Next we have volume percent, or percent by volume. I like the V over V because that tells you that the guy in the top is measured by volume and the guy in the bottom is measured by volume. Again, any percent subject over total times 100%. The difference is now we have the volume of our subject, which is the solute, over the volume of our total, which is the solution. The last one is an oddball, mass volume percent. And the reason this is an oddball, well, first, the reason this is an oddball is because, is there any mass unit that will cancel a volume unit? And the answer is no. So because we can't just put grams over grams or milliliters over milliliters, since we have to have we end up having to have a set unit, because you can't just put any mass unit over any volume unit, that wouldn't make sense. You get all kinds of different answers for your concentration for the same solution. And so here we are limited to only the mass unit of grams over the volume unit of milliliters. And again, this is an oddball because a true percent, the unit should cancel, and you get that percent from the times 100% at the end. Okay, let's do a few examples, and we're told a solution is made with 20 grams of sodium sulfate and 200 grams of solution, and we're asked for the mass percent. Okay, we are using an equation here. Any percent subject over total times 100%. We know our subjects are solute. Our totals, that's just that, the total amount of solution. And the m over n tells us these are measured by mass. So what goes in the top? The 20 grams of sodium sulfate. And what goes in the bottom? The 200 grams of solution. And that gives us a 10% mass sodium sulfate solution. And if you ever make a solution, make sure that you label it with that m over m. Or if you're using a solution and it's supposed to be mass, look to make sure that you see that m over m. There can be a significant difference between m over m and v over v. Next we have a solution made from 25 grams of sodium chloride and 100 grams of water. What is the mass percent? Well, still using our equation, any percent, subject over total times 100%. Our subject is our solute, and it's measured by mass, and our total is the amount of solution, and it also is measured by mass. What goes in the top? The 25 grams of sodium chloride. And what goes in the bottom? Let's be a little more careful here. If you're saying 100 grams of water, I would ask you, is that the total? No, the total is 125 grams of solution. Note here we were given water, we weren't given the solution. If you're given the solution, that would be the total. But if you're given water, you're just given the other component of your solution. And you'd have to add in the solute. Sometimes we have a third number that's missing, and that's the total. Let me give you an example. I've got a class that's 5 men and 10 women. What's the percent of men? Well, that's 5 divided by 10 times 100%. And 5 over 10 times 100% is 50%. Is that right? 5 men, 10 women, the class is 50% men. Well, I didn't divide by the total. So make sure that you're identifying your total correctly. So that's 20% mass sodium chloride solution. And again, do put in that MM or VV or MV or whatever the appropriate unit is. Okay, next a beer is found to have 10 milliliters of alcohol and 200 milliliters of beer. What is the V/V percent? Okay, again, any percent equals your subject over your total times 100%. Our subject is the amount of alcohol, and it's measured in volume. And then the total is the total amount of solution, which would be the total amount of beer, and that also would be measured by volume. So the 10 milliliters of alcohol goes in the top. We never get messed up with the top. And what goes in the bottom? Is that going to be just 200 milliliters, or is it 200 plus 10? Does the beer that you buy come with the alcohol already in it? Yes, it does. So that 200 milliliters of beer is the total. Or a 5% V/V alcohol solution. And it is important that we put in the V/V or M/M. Let me give you a quick analogy to help us realize why this is important. Now, I used to make my own beer, and when I did, I would have some friends over and share my beer, and I would give a beer to them and say, let's say I have the guys coming over, and I say, here's a beer, and it's 5% alcohol, and they would say that's great, they would drink it, and they'd be happy. Then, the next night, my wife would have some friends over, and ladies usually don't like that high alcohol, so I'd tell them it was 4% alcohol, and they would drink it and say it was good, and they'd be happy. It was the same beer. So how can it be 5% and 4% simultaneously? Well, it's actually 5% by volume and 4% by mass. The difference is because there's a 27% difference between the density of alcohol and water, is why there's a 27% difference between mass and, mass and volume. So this is just trying to illustrate that these can be significantly different. Again, that's a 27% difference. So make sure you label when you're making up solutions, and a good chance you'll be making up solutions somewhere in your future. Or if you're using solutions, make sure that you identify you're using the correct solution. Okay, any concentration term, just like any dual unit term, can be used as a conversion factor. Remember how miles per hour takes it between miles and hours? Well, percent will take us between amount of solute and amount of solution. Now, from an 18% mass potassium chloride solution, I get the conversion factor 18 grams of potassium chloride per 100 grams of solution. We need to be able to take a given percent and pull it out and identify it as the conversion factor that we have here. Now, it's actually kind of neat the way that these roll off your pencil. Let me illustrate this. Now, I would have began with 18% mass potassium chloride solution. Note my little arrow here. 18% mass KCl solution. 18% mass KCl solution. Top, bottom, top, bottom, top, bottom. Kind of interesting the way it just rolls off of your pen that way. One way or another, we need to come up with that 18 grams of potassium chloride per 100 grams of solution, because those are going to be our tools for converting between amounts of solute and amounts of solution. Okay, let's look at an example here. How much glucose must be added in order to make 500 milliliters of a 10% mass volume glucose solution? Okay, let's go all the way to the beginning. We got a calculation before us, equations or units, and I'm not remembering any equations, so units. Do I have any preliminary steps? And we want to pull out that conversion factor. And that 10% mass volume glucose, 10%, follow along, 10% mass volume glucose solution. Top, bottom, top, bottom, top, bottom. Okay, so we pulled out our conversion factor, our tool, and I think we're ready to get started. So we're using our units, and that means step one, what are we after? How much glucose? How much glucose? Well, what unit's going to go along with glucose? Well, let me look back to my conversion factor, and I see grams is associated with glucose. So that's what I'm after. So actually, having pulled out that conversion factor from the beginning already helped me out in step one. Is it going to help me in step two? It sure is. We now can see it clearly that 10% isn't a single unit. So the 500 milliliters is what we're starting with. The only number up there with a single unit attached. So it helped us for step two. Is it going to help us in step three as well? Well, let's go on to the beginning. Out of milliliters of solution. And here comes the big question. Can we go straight from milliliters of solution to grams of glucose? Let's look at our conversion factor. Oh, we most certainly can. So it helped us in step three. And it's also going to help us in step four. Where do those numbers go? Well, that 10 goes with the grams of glucose, and it doesn't matter if it's on the top or on the bottom. And the 100 goes with the milliliters of solution. And again, it doesn't matter if that's on the top or on the bottom. So actually, having pulled that conversion factor out from the beginning helped me in all four steps. And now, putting this on my calculator, I come up with 50 grams of glucose. Now do note, if you're ever going to make up a solution, this is the first question that you're going to be faced with. You know the concentration of the solution, you know the volume that you need, so how much solute are you going to measure out? So do note, this is a very practical question. The more practical it is, the more likely it's going to come up again in your future. And I'm talking about your own personal future. If it's classes in your future or your future profession. Okay, how much of a 15% mass sodium iodide solution can be prepared from 60 grams of sodium iodide? Okay, again, got a calculation before us. Equations are units, and it's still units. Any preliminary steps? You guessed it. Let's pull out that conversion factor. Okay, and on to step one, we're after how much sodium iodide solution. So is that grams of solution, milliliters of solution? Well, let's look at our conversion factor. And it says grams of solution. Okay, on to step two. There's only one number up here with the single unit, isn't there? That's 60 grams of sodium iodide. And now time for step three. Let's get out of grams of sodium iodide. Can we go straight to grams of solution? And with that conversion factor sitting right there in front of us, I hope we see that's an easy yes. And it's also easy to see where those numbers go. This time the 15 is with the grams of sodium iodide, which is on the bottom. Numbers always go with specific units. It's never a matter of this number is always on the top or this number is always on the bottom. And that looks like 400 grams of solution. And again, feel free at any time to pause the presentation so that you can do some of these on your own. And I'm expecting that you are doing that on a regular basis. If this was in a face-to-face class and a lot of these problems, I would be stopping and letting students have an opportunity to do them on their own. Okay, well, we've got a calculation before us. Equations are units. Still using our units. Any preliminary steps? Pulling out those conversion factors. Then, step 1, we're after how much sodium hydrogen carbonate. We know to go and look at the conversion factor to see that's going to be in grams. And then for step 2, we're going to start with that 2 liters of solution, the only number up there with a single unit. And now time for step 3. Let's get out of liters of solution. Now comes the big question. Can we go straight from liters of solution to grams of sodium hydrogen carbonate? Let's look over here at our conversion factor. No, I first need to be in grams of solution, and I see there's a mistake here. That actually should be milliliters of solution. So that should be 20 grams of sodium hydrogen carbonate over 100 milliliters of solution. So do go back and make that correction. Can't make that correction now, but you need to correct that in if you wrote it down as grams. Okay, because we're going to go to milliliters of solution, and then from milliliters of solution we can get into grams of sodium hydrogen carbonate. 1 milliliter, 10 to the negative third liters, and that's 20 grams of sodium hydrogen carbonate per 100 milliliters of solution. And I produce an answer of 400 grams of sodium hydrogen carbonate. I'm going to write in this form to illustrate that 2 significant figures is appropriate. Okay, the next concentration term is molality. Kind of sounds a little bit like molarity, but it's not, and it's not capital M bar, it's lowercase m bar. Now we can see why it looks so similar to molarity, because it is based on moles of solute, but it's not based on liters of solution, it's based on kilograms of solvent. And this is unique about the molality concentration term, that it's not based on the amount of solution, it's based on the amount of solvent. And because of this, we can actually generate some pretty high molality concentrations. And by that I mean into maybe 20, maybe even 30 molal concentration, much more than molar. Okay, well, just like we've done before, we're going to use our units to set up these calculations, so let's go ahead and jump into an example. We're told a solution contains 34.2 grams of sodium hydroxide and 452 grams of water. What is the molality of the sodium hydroxide solution? Okay, we're using our units. Do we have any preliminary steps? Can't think what that would be. So on to step 1. Molality means moles per kilogram. Moles of your solute per kilogram of solvent. The majority of the time that solvent's going to be water. There is one lab we're going to do where it's actually not going to be water, though. It'll be an alcohol. Okay, well anyway, if we're after 1 unit per another, then for step 2, we're starting with 1 unit per another. I see 2 single piece information up there, grams of sodium hydroxide and grams of water, which should go on the top and take us to moles of sodium hydroxide. 34.2 grams of sodium hydroxide. And what's going to take us to kilograms of water? 452 grams of water. Okay, I need to take care of both of these units. So first, let's take care of our numerator. So out of grams of sodium hydroxide, And here comes our big question. Can we go straight from grams to moles? And I hope that's an easy yes for you. There's our most common calculation component in all of chemistry, going back and forth between grams and moles. Okay, so let's scratch out the grams, circle the moles. So we've got our numerator for our denominator out of grams of water. Can we go to kilograms? Well, certainly that's just a metric conversion. Molar mass of sodium hydroxide, 23.0 plus 16.0 plus 1.0 for 40.0 grams per each mole. And 1 kilogram, 10 to the positive third grams, based in number, still going with the base unit. And when I put this all on my calculator, I come up with a 1.89 molal solution. Okay, the next concentration terms are parts per million and parts per billion, and these actually have a very similar form to percent, which are actually parts per hundred. So do note, if we had percent, it would be subject over our total times 100, that's cent as in percent, but for parts per million, it's the subject over the total times a million. And for parts per billion, you're subject over your total times a billion. And just like we had for mass percent and volume percent, the units simply have to be the same. So just keep that in mind. The units have to cancel. They need to be the same so that they can cancel. Okay, let's do an example. Oh, looks like we'll do one later. Let me move on to dilution, and we'll do some more examples in a bit. Okay, first, dilution is the phenomenon that occurs when you add additional solvent to an already existing solution. What happens when you add more solvent? So think of that glass of iced tea, and you added more water to it. Well, as the volume went up, the concentration went down. Now here's a nice visual illustrating this phenomenon. The flask over on the left we see is the more concentrated solution, and we can see all those particles quite close to each other. Then the one on the right, we simply added water to the original solution, and it pushed those particles further apart. So we can clearly see the one on the left more concentrated than the one on the right. By adding more solvent, we were able to spread out those particles more, and hence the concentration was reduced. We can also easily see that by just looking at the concentration term of moles per liter. Well, let's say I had 1 mole in 1 liter, and then doubled my volume and went to 1 mole in 2 liters. Well, then I just went from 1 molar to 1/2 molar. What we're going to find is as your volume goes up, your concentration actually goes down by the same factor. So if you doubled your volume, you would half your concentration. If you tripled your volume, you'd 1/3 your concentration. 10 times your original volume, 1/10 of your original concentration. And that'll hopefully give us some way to predict if our answers are on the mark. Okay, now just because it's going to be important is note that the amount of solute is not changing when we dilute a solution, and that should be obvious. We're not taking any solute out. Okay, let's generate the general dilution formula together, and it begins by recognizing that the amount of solute is going to be equal to the product of the volume and the concentration. Now let me start with the amount of solute in moles. N represents moles. And when I use my volume in liter and my concentration in moles per liter, we can see, sure enough, volume times concentration, where the volume is liters and the concentration is moles per liters, gives us the amount of solute in moles. Let me clarify that the sub C's there, the subscripts, refer to concentrate. So let's just say that when we began with our undiluted solution, that the number of moles of solute in there would be equal to the product of the volume and the concentration of that solution. Okay, then what happened when we diluted that solution? Well, it turns out that the number of moles of solute is still equal to the product of the volume and the concentration, only now we're talking about the volume of the dilute and the concentration of dilute, and hence those subscripts of D refer to now that it's dilute. Now, what did we say about the amount of solute earlier? Was the amount of solute changing in dilution? No. And since the amount of solute remains unchanged, then you know where we're going with this. And the number of moles is equal to the product of the volume of the concentration and the molarity of the concentration. And it's also equal to the product of the volume when it's dilute and the molarity of the dilute. Then obviously we can set those two equal together since they both equal the same thing. And that gives us our general dilution formula. And note how we just generated it fairly easily on our own. So in a pinch, hopefully you can generate it again. Okay, now a more generalized version of this would be V sub C times C sub C equals V sub D times C sub D, in which case it doesn't really matter what concentration term you're using. Now this really doesn't work well with molality because it's really not based on the volume of your solution. But for pretty much everybody else it would be pretty close. Even mass you would get kind of close. But mass volume, volume, molarity, this works great. Okay, let's go through an example. We're asked to what volume should 150 milliliters of 5 molar acetic acid be diluted to give a 0.1 molar solution. Okay, now let me share with you the way that I approach these problems. In a normal problem like this where I'm going to be using an equation, I would start with, are there any preliminary steps, identify those preliminary steps, and then get to the equation. When I'm using my units and I have a preliminary step, again, I always start with preliminary steps and then I would get to my units. This is going to look a little bit different because as part of the preliminary step, I'm going to pull out the equation. And the reason that I do that is because I want to first go ahead and identify what the information is that's given in the problem. This is a little bit different than the normal way that we approach a calculation using an equation. Normally we would break out the equation, solve for the variable we're after, and then plug everybody in, and if we're missing some variables, set up additional equations. But the reason that I'm going to do it this way is because sometimes it's not really obvious what you're given and what you're asked for. And so that's why we're going to do it in this fashion. At least let's do it once this way. I want to identify what all that information is. What's that 150 milliliters? Well, I think it's obvious it's some type of a volume term. What's that 5 molar? Some type of a concentration term. And the 0.1 molar, another concentration term. So we've at least identified the dimensions that are being measured. We just need to identify, is it sub C, is it sub D, which is it? Now that's not going to be too tough if we follow this procedure or this approach. So first we identified volumes and concentrations, and then what we're going to do to help identify which is which is we go to the two in the same unit. So we have two molarities here, two concentration terms. And now based on the size, I should be able to tell which is which. So for this bigger concentration term, that 5 molar, that's the bigger one. Which is it? Which is the bigger concentration? The concentration of the concentrate or the concentration of the dilute? When is our solution more concentrated? Before it's diluted or after it's diluted? And I hope you said that the bigger concentration is the concentration of the concentrate. The lower concentration is actually the result of the dilution. Adding more water, we reduce the concentration. We diluted it. Okay, so at least I've identified the different concentration terms. What about that volume term? Well, we often have key words like of and from and is that would tie these together, meaning tie that unknown volume or concentration to somebody else. And so do note, this is 150 milliliters of the 5 molar solution. Well, if the 5 molar solution is concentrated, then that 150 milliliters must be the concentrated as well. So I hope that following this approach, you found it very easy to identify what all that information is. And now that we've identified what that information is, just by the process of elimination, we should be able to identify what we're after. So what is the missing variable? The volume of the dilute. Now, we didn't have to do it this way, but this does help give you an additional way to confirm what is it that you're after. Okay, we're after the volume of the dilute. I'm going to first just flip the equation around, then divide out the molarity of the dilute, and here's the volume of the dilute isolated. And because of the way that we started the problem, we already have these variables identified, so we're ready to go ahead and plug them in. Now, even though we didn't use our units to set up the calculation, do note all units should cancel but a unit that we should have. So do note how both of those molarities cancel, leaving us with the appropriate unit of milliliters. And when I put this all on my calculator, I come up with 7,500 milliliters. I started with 150 and I'm left with 7,500. That's a huge increase in volume. Well, do note the concentration was reduced 50-fold. And how do we reduce the concentration 50-fold? By increasing the volume 50-fold. And so, yes, this really does look to be right. Okay, let's do another. How many milliliters of a 12 molar ammonia solution are needed to prepare 75 milliliters of 1 molar ammonia by dilution? Okay, I'm going to go ahead and use that same approach. I'm actually still working on a preliminary step. I want to identify what all that information is. But as part of the preliminary step, I'm going to break out the equation. Because these three pieces of information, concentration term here, volume term here, concentration term here, these three pieces of information are three of the four variables in that equation. So that's why I start with the equation. So I essentially know what potentially this information is. Okay. And now we're halfway done with identifying who's who. The other half is to identify which is which. In other words, we've identified the dimensions being measured. Now we need to figure out, well, who's concentrated and who's dilute. So once again, we go to the two units that are, the two values that are in the same unit, meaning the two concentration terms. And the bigger concentration is which? The concentration of the concentrate or the concentration of the dilute? Think of the picture of those two flasks. The one on the left was concentrated, the one on the right was dilute. The greater concentration was greater concentration is the concentrated solution. The lower concentration is the result of dilution. So I hope there's no head scratching or any stumbling to get here. And now, what about that volume term? What does that 75 milliliters go along with? Well, that's 75 milliliters of the 1 molar, and that's dilute, which means this volume is also dilute. And now we've identified the three variables, or the three informations that we're given, what variables they are, and hence the three variables of the four, and the fourth variable this time is the volume of the concentrate. So that's ultimately what we're after. Now, if we read the problems real carefully, we should be able to identify that's what we're after. Just like in the last problem, if we read the problem real carefully, we should identify the volume of the dilute was what we're after. Okay, we're after the volume of the concentrate. Let's divide out the other guy. So we'll divide out the molarity of the concentrate. And here's the volume of the concentrate isolated. And we just identified these three variables, so we're ready to go ahead and plug them all in. And when I put all this on my calculator, I come up with 6.25 milliliters. Do note the unit's what I need, milliliters. So even though our units aren't setting up the problem, they're still there to help us catch small, simple mistakes. And we'll see many of those. Okay, does my answer make sense? Well, hold on, I've got a smaller volume. Well, this would be what you started with. You started with 6.25 milliliters of the 12 molar ammonia, and then diluted it to 75 milliliters, and at that point had 1 molar ammonia. So I hope having said it that way, the answer makes sense to you. Okay, one more. A sodium chloride solution is 2 molar in concentration. Find the molarity when a 10 milliliter sample is diluted with water to a volume of 40 milliliters. Okay, same approach. We want to identify what all that information is, and we begin with the equation. I see a concentration term in that 2 molarity, a volume term in that 10 milliliters, and another volume term in the 40 milliliters. Okay, so we're halfway done identifying these variables. What's next? I hope you said to compare the two in the same measurement. So we have 2 volumes, and so the bigger volume is which? The volume of the concentrate or the volume of the dilute? When do I have the greater volume? Before I dilute it or after I dilute it? And I hope you said after. The bigger volume is the volume of the dilute. The smaller volume was back when it was concentrated. Again, think of those 2 flasks. The one on the left, dark red, small volume. The one on the right, light red, high volume. Okay, now, what about the molarity? Well, let's see. Is that 2 molar of 10 milliliters? Maybe I should say it the other way. Is that 10 milliliters of the 2 molar solution? Or is that 40 milliliters of the 2 molar solution? And I hope that you saw that that's 10 milliliters of the 2 molar solution, which means that this is also concentrate. Now, what if we ever get stuck? Let me go back. What if we get stuck? I don't know which term this is. Is that concentrate or dilute? Well, we can, at this point, just read the problem carefully. Find the molarity when the sample is diluted. Find the molarity when the sample is diluted. So what are we after? The molarity of the dilute. And I hope that would make it clear that what we're given then must be the other guy, the molarity of the concentrate. Okay, we identified that we're after the molarity of the dilute. Let's divide out the volume of the dilute. And here's the molarity of the dilute isolated. And again, the good thing about the approach we just take is we're ready to plug everybody in at this point. And note how the 2 volume terms cancel to leave us with the appropriate unit of molarity. And I get a 0.5 molar solution. Does that make sense? Well, let's see. My volume went up 4-fold, and the concentration went down 4-fold, so it absolutely makes sense. I mean, it makes sense to the point where I not only make sense, but I have confidence that it must be this answer. Sometimes I just have an idea by the size of it makes sense, but here I can actually get right down to, yes, 1/4 of 2 molar. Okay, I want to go over the relationship between concentration terms and how can we convert between them. Now, ultimately, any of those concentration terms gave us a conversion factor. If it was mass percent, or molarity, or molality, each of those gave us units. And so we're simply going to start with those units. I think I can illustrate this easiest through an example. So, here, concentrated phosphoric acid is 85% phosphoric acid by mass. The density is 1.689 grams per cubic centimeter. And we're asked to calculate the molarity and the molality of the phosphoric acid. Okay, so let me illustrate the approach. This is purely an exercise in units. I can't say that enough. This is purely an exercise in units. So, step 1, what are we after? We're going to do molarity first, so what are the units of molarity? Moles per liter. We make it clear, that's moles of phosphoric acid per liter of solution. I think it would be okay if I just put moles per liter, but it never hurts to be fully thorough and label everybody thoroughly. Okay, well, if we're after 1 unit per another, what's that tell us about step 2? We're starting with 1 unit per another. And what we're starting with is the already existing dual unit conversion factor that 85% phosphoric acid actually gives us. If we're going to build a conversion factor out of that 85% phosphoric acid by mass, we would have 85% mass phosphoric acid solution. In other words, we're going to get the exact same thing we see here over on the left. In other words, we start with the conversion factor that our concentration term gives us. Okay, on to step 3. Let's get out of grams of phosphoric acid and ask the big question. Can we go straight from grams of phosphoric acid to moles of phosphoric acid? We most certainly can. Then let's get out of grams of solution. We already have our numerator. And I would recommend that you scratch out those grams of phosphoric acid. Circle the moles of phosphoric acid. Okay, now out of grams of solution, can I go straight to liters of solution? Okay, I need to go from mass to volume. How do I do that? Through a given density term. And so we're going to go from grams of solution to cubic centimeter, but remember, a cubic centimeter is the same as a milliliter, so I'm going to save myself a little bit of chicken scratch and just convert that mentally. Then from milliliters of solution, we can go to liters. Okay, it turns out the molar mass of phosphoric acid is 98.0 grams per each mole. And that 1.689 grams per cubic centimeter is 1.869 grams per 1 milliliter. Remember, 1 cubic centimeter is exactly 1 milliliter because of the way that the metric system was designed. Those are an exact relationship. And then base 10 number, still going with the base unit, 1 milliliter, 10 to the negative third liters. And when I put this on my calculator, I come up with 14.6 moles per liter. Does that seem correct? That seems pretty high, and I'll just go ahead and mention this if I haven't before, that the highest concentration term that I'm aware of in molarity is about 18 moles per liter for concentrated sulfuric acid. It's only about 11 moles per liter for concentrated hydrochloric acid, 12 moles per liter for ammonia, and now we see 14.6 moles per liter for concentrated phosphoric acid. So for something to be cut, well, anyway, my tie-in is less than 20. Let's just keep it that way. Nice easy number, less than 20. And if it's concentrated, I expect it to be, say, between 10 and 20. Okay, on to the calculation for molality. We're still using our units. This time the units we're after is moles per kilogram, moles of phosphoric acid per kilogram of water. And just like before, if you're after 1 unit per another, you're starting with 1 unit per another, and we're going to start with that same 85% mass phosphoric acid solution. Let me bring out my hand. 85% mass phosphoric acid solution. Okay. On to step 3, and by the way, we could have started with the just calculated 14.6 moles per liter that we just got. All right, on to step 3, out of grams of phosphoric acid, and can we go straight to moles? Certainly. Let's scratch out those grams of phosphoric acid and circle the moles. So now that tells us we need to get out of grams of solution. That's going on the top. Can we go straight from grams of solution to kilograms of water? We might think we can, but what's the one on the top here? Grams of solution. What's the one on the bottom there? Kilograms of water. Can we go from grams of solution to kilograms of water? No, we need to be in grams of water, not grams of solution. Can you go straight to grams of water from grams of solution? And yes, we can, and I'll show you in a minute where we're going to get those numbers. Then, out of grams of water, can we go to kilograms of water? And yes, we certainly can. Okay, let's scratch out everybody that canceled, circle what's left, and sure, what we're left with is moles over kilograms. Always do that double check. It's just so easy to miss something, and it's really easy to catch it. I just got done grading a whole bunch of exams yesterday, and I saw many instances where students were putting in all these units, and then they wouldn't go through and scratch them when they were done and circle what was left, and they wouldn't all work out. Whereas I'm 100% confident they have taken just 5 seconds to scratch out those units that cancel, they would have realized their mistake and corrected the problem. Okay, on to step 4, bringing in the numbers. 1 mole of phosphoric acid, the same 98.0 grams. Okay, now grams of solution to grams of water. Now, where am I going to get that? Well, let's go back to the concentration term. If I have, well, what's in my solution? Phosphoric acid and water. There's just those 2 components. So if it's 85% phosphoric acid, then it must be 15% water. Again, if it's 85% phosphoric acid, then it must be the remaining 15% water. And then base 10 number, still going with the base unit, 1 kilogram is 10 to the positive third grams. And the first time I hit equals and came up with 57.8 grams, I hit erase because I thought I made a mistake and did it all again and got 57.8 again and thought this is just too big. And so I went back and double checked and double checked and double checked, and then I realized I was thinking about molarity. Molality can get much higher. Why can molality get so much higher? Because of this term right here. The amount of solvent per amount of solution can decrease significantly. Meaning when you get really high concentrations of solute, which would mean low concentrations of water. That's why we generate such a high value for our concentration in molality. Okay, let's practice some of the things that we've just gone over. First, a solution is made with 28 grams of potassium sulfite and 400 grams of solution. What is the mass percent? Okay, percent, we're using an equation. Subject over total times 100%. Our subject is always our solute. The total is always the total amount of solution. And that's measured, both are measured by mass. So we're looking for the mass of the solute to go on the top. And that would be the 28 grams of potassium sulfite. And the total amount of solution to go on the bottom, the 400 grams of solution. And do note there's a difference between when you're given solution and given water. If you're given water, you have to add in the solute. If you're given solution, that's your total. And by the way, if you're given in the beer, in the vinegar, that also would be your total. So I come up with a 7% mass potassium sulfite solution. And again, if you're making up solutions, please make sure you put in that M/M. Or if you're using a solution, double check, is that M/M? Or is it something else, like B/V or M/V? And I illustrated earlier, there can be a significant difference between them. Okay, a solution is made from 50 grams of magnesium oxide and 200 grams of water. What is the mass percent? Again, any percent, subject over total times 100%. Your subject's your solute, your total is your total amount of solution. And again, they're both measured by mass. What goes on the top? The 50 grams of magnesium oxide. And what goes on the bottom? And I hope you said 250 grams of solution. For a 20% mass magnesium oxide solution. Next, vinegar is found to contain 22 milliliters of acetic acid and 500 milliliters of the vinegar. And we're asked for the volume percent. Still, any percent, same equation, subject over total times 100%. The difference is now both of those are measured by volume. So, the volume of the solute goes on the top, and that would be the 22 milliliters of acetic acid. And the volume of the solution goes on the bottom, and that's going to be 500 milliliters of solution. That 500 milliliters of vinegar does contain the acetic acid. And that gives us a 4% volume acetic acid solution. Okay, a solution contains 124 milligrams of silver and 400 grams of solution. What is the concentration in parts per million? Well, parts per million following a very similar setup as parts per hundred. Your subject over your total times a million. And just like anybody else, those units have to cancel, so they have to be the same. So, I'm going to convert that 124 milligrams of silver into grams of silver. so that the grams of the silver and the grams of solution can cancel. And when I put this on my calculator, I come up with 310 parts per million of the silver ion. Note how similar these are to percent calculations. Next, a solution contains 0.0671 milligrams of the lead 2 ion and 2.50 kilograms of water. What is the concentration in parts per billion? Parts per billion, like parts per 100, your subject over your total only times a billion. Our subject is our solute, so that's going to be the lead 2 ion. Our total would be the total amount of everything. And again, these need to be in the same unit. So let me convert both milligrams of lead and kilograms of water to the base unit of grams. Base unit is just the easiest unit to convert anybody into. So that 0.0671 milligrams of lead is 0.0671 times 10 to the negative third grams of the lead. And that 2.5 kilograms of water is 2.5 times 10 to the third grams of solution. Now, how did I get from grams of water to grams of solution? Well, do note that if I added in that 0.0671 milligrams of lead, I'm going to have to go something like 7 digits down to the right to see that number show up. In other words, it just got swamped by the huge mass from the water. And that gives us 26.8 parts per billion for the lead 2 ion. Okay, the unit 12% mass ammonia converts between what two quantities? Well, between grams of ammonia and grams of solution. And what two conversion factors do you get? Well, let's see, I'm going to have 12 grams of ammonia over 100 grams of solution. And the other would simply be this flipped upside down, so you have the 100 grams of solution over the 12 grams of ammonia. 12% mass ammonia solution. Remember how we built those in the past. And the unit 12 molal ammonia converts between what two quantities? Well, what are the units in molality? Moles of solute per kilogram of solvent. So what two conversion terms do you get? Well, that would be 12 moles of ammonia per 1 kilogram of solvent, water in this case, and the others simply the first inverted. So you have 1 kilogram of water over the 12 moles of ammonia. And we'll know which one we need when we get there. So we don't have to ever scratch our head before then. We'll know what we need to do when we get there. That's a great thing about units. And how is a solution diluted? Let's see. Well, the concentration goes down. Do we remove solute? No. We dilute a solution by increasing the volume. So adding more solute, so the total volume of the solution goes up. And what happens to the concentration of a solution when it's diluted? The concentration goes down. And I already answered this. Is the amount of solute decreased? No. It's just spread out more. Okay, how much of a 5% mass sodium chloride solution can be prepared from 12.5 grams of sodium chloride? Okay, well, we're using our units here, or are we? Well, actually we are. Let me make a comment here. If you're calculating percent, we'll use the equation for percent. But if you're given a percent, you're being given a conversion factor. And we're back to using our units. Okay, so I hope we realize we're going to use our units. Do we have any preliminary steps? And I hope you said, let's pull out that conversion factor. Okay, on to step 1. We're after how much solution, So what's the unit I need for much? Well, as we look at the concentration term, we see the amount of solution is measured in grams. Step 2, only that 12.5 grams of sodium chloride is a single unit. And here comes step 3. And I hope that you're still finding step 1, step 2, the beginning of step 3 is a total no-brainer. Again, nothing has gotten complicated to where step 1, step 2, or the beginning of step 3 has increased in complexity or difficulty. And yet, just like before, we are well on our way. We're like halfway done, if not more, with our problem. So if you've been avoiding diving in and using your units, you really need to change your ways. I'm providing you with probably one of the best tools you'll ever have. But just like any tool in your toolbox, if you never use it, it isn't worth anything. Okay, here comes the big question. Can we go straight from grams of sodium chloride to grams of solution? And that concentration term sitting right there in front of me makes the answer obvious. Yes. And for step 4, it also tells me where those numbers go. The 5 is with the grams of sodium chloride, the cent with the grams of solution. For 250 grams of solution. Next, how much glucose must be added to make 400 milliliters of a 5% mass volume glucose solution? Again, we've got a calculation before us. Again, we're going to be using our units, any preliminary steps, and again, let's pull out that conversion factor. Then on to step 1, we're after how much glucose. So what unit are we after? Grams of glucose. And again, we got that from our conversion factor. That's why it was a good idea to do that at the very beginning before we did anything else. Step 2, we're looking for a number with a single unit to start the calculation with. Only one of them up there, the 400 milliliters of solution. And here comes the beginning of step 3. Let's get out of milliliters of solution. Here comes the big question. Can we go straight from milliliters of solution to grams of glucose? Yes, we most certainly can. Our setup is complete. And that's 5 with the grams of glucose and cent with the mils of solution. Or 20 grams of glucose needing to be measured out. Next, what is the molarity, not molality, what is the molarity for 20 grams of sodium hydroxide in 250 milliliters of solution? I don't think I have any preliminary steps here, so step 1, I'm after molarity. And don't ever just use big M bar, you'll find yourself stuck every time. We need to identify what that means, moles per liter, and if we're after one unit over another, then we're starting with one unit over another. Okay, we have two single piece of information, grams of sodium hydroxide in milliliters of solution, which is going to go on the top and take us to moles of sodium hydroxide. Grams of sodium hydroxide. And that leaves milliliters of solution to go on the bottom. Does that seem right? Yeah, milliliters is going to take us to liters. Okay, and on to step 3, let's take care of our numerator first. So out of grams of sodium hydroxide. Can I go straight from grams of sodium hydroxide to moles? We most certainly can. And there's our numerator. Still need to work on our denominator, so out of milliliters of solution, can we go to liters? Absolutely, that's a simple metric conversion. And for the molar mass of sodium hydroxide, I have 23.0 for the sodium, 16.0 for the oxygen, and another 1.0 for the hydrogen, which adds to 40.0 grams per mole. And base 10 number is still going with the base unit. I also saw in that exam a lot of people putting their base 10 numbers with the prefixes, and obviously that's always going to give you the wrong answer. This gives me a 2 mole per liter solution. And I might ask, does this seem right? And I have every reason to say that it does. And how many grams of sodium chloride would you need to prepare 1.25 liters of a 0.1 molar sodium chloride solution? Okay, I'm pretty sure I'm still using my units. Any preliminary steps? let's pull out that conversion factor. Then, step 1, how many grams of sodium chloride? Step 2, looks like we're starting the calculation with that 1.25 liters of solution. Now time for step 3, let's get out of liters of solution. Now comes the big question, can I go straight from liters of solution to grams of sodium chloride? No, but as we look at the conversion factor, we can see we're going to get the grams of sodium chloride from moles. So let's first go from liters of solution to moles of sodium chloride, and then from moles of sodium chloride to grams. We get 0.100 moles of sodium chloride per each liter of solution. And then the sum of 22.99 and 35.45, we have 58.44 grams per each mole, or 7.31 grams. Does our answer make sense? And I'm going to say yes. Now, what type of answers don't make sense? How about 7 times 10 to the negative 6 grams? Or 7 times 10 to the net positive 6 grams, or even just 7 times 10 to the positive 3rd, or even 731. All of those would seem to be outside of a reasonable size. So am I absolutely sure that it's 7.31? No, I am never allotted that luxury. I just know that it's not an obviously wrong answer, and that's the ones we want to catch. Okay, next to what volume should 50 milliliters of 1 molar acetic acid solution be diluted to give a 0.1 molar solution? Before we begin this, let's go ahead and come up with the answer just from the concept of, or from our previous work. Okay, now, what's our concentration going to do? It's going to go down by a factor of 10. From 1 molar to 0.1 molar, our concentration is going down by a factor of 10. So let's go ahead and make a prediction. What's going to happen to our volume? Well, the concentration is going down by a factor of 10. That's going to be due to the volume going up by a factor of 10. So I'm already predicting 500 milliliters. I don't want you to do this in your head and give your answer like that. I want you to do the calculation, but I want you to have some idea, when you can, beforehand, of what a reasonable answer is. Okay. Now, to help us identify all those pieces of information in the problem, we're going to break out our equation. And then I think it's quick and easy to identify the dimensions being measured, the volumes and the concentrations. And now, which is which? Which is concentrated and which is dilute? Like we've done before, and I hope you know what we've done before. What did we do before? We compared the two in the same measurement. We have 2 concentration terms here, so let's compare them. The bigger concentration, that 1 molar, is which? Is that the concentration of the concentrate or the concentration of the dilute? Concentrate. The dilute is always the result, the lower concentration is always the result of dilution. Okay, do I have any keywords to tie that volume to somebody? Of. It's 50 milliliters of the 1 molar. And since that's concentrate, then this is concentrated as well. And so it looks like we're after, what's the missing variable? The volume of the dilute. Let me flip my equation around, divide out the molarity of the dilute, and here's my equation isolated for the variable that I'm after. And I've already identified all of these variables to plug in. Now you surely don't have to approach this in this fashion. You can do the normal, break out your equation, isolate the variable you're after, identify the variables and plug them in. But either way you do it, I hope that you find this successful. And there's that 500 milliliters that we were predicting. So you don't need my method, but you do need a method. And I just presented you with one that works very well. Okay, that concludes this lecture, where chapter 10 is on solutions. And we learned some of the other concentration terms. Back in chapter 4, we learned about molarity. Today we learned about percent concentrations, mass, volume, and mass volume. We learned about molality. We learned about parts per million and parts per billion. We also learned about dilution and how to convert between all the different concentration units. And that concludes this lecture.